Okay, welcome you all for today classes. Uh, for our first model, we are going to solve some problems on heat conduction equations. Okay, uh, today we will solve some problems. That first, in that first we have to take first one. So consider a one-dimensional steady-state heat conduction in a plate with a constant thermal conductivity in a region 0 to L. Okay, a plate is exposed to uniform heat flux Q watt per meter square at x equal to 0 and dissipates the heat by convection at x equal to L. Okay, with the heat transfer coefficient H to the surrounding air at TA. Okay, write the mathematical formulation of this problem for a determination of one-dimensional steady-state temperature distribution within the wall. Okay, so this problems is based on the formulation of this problem. Okay, so we need to create some formula based on the given data. Okay, it based on the given data. Okay, see here, whatever first what he has given, consider a one dimensional steady state. So one dimensional steady state is nothing but what, here d square t by dx square. One dimensional, that is direction of this plate is in, the heat flow is in only one direction, that is in, we have to take it in x directions only. We have to take it in x directions only. Okay, he has given one plate with a constant thermal conductivity. The thermal conductivity, that is Kx is equal to Ky is equal to Kz is equal to K. That is constant thermal conductivity he has given. And the reason he has given, when x equal to 0 to x equal to L, that is 0 to L. This is the reason. In the within this region, the plate is in capped. One plate is capped, and that is having only one dimensional steady state heat conduction. Steady state heat conduction. Steady state is nothing but that change in temperature with respect to time is 0. Okay, so that is the steady state heat conduction. Okay, a plate is exposed to the uniform heat flux Q. So here, if you are consider this figure, the plate here, there is one plate with a thickness of L. Okay, so this is the 0 to and x, this is x directions. Okay, so here at this point, when x equal to 0, that is the range here, and here at this point x equal to L. Okay, a plate is exposed to uniform heat flux Q. So here it is a uniform heat flux which is exposed, this surface is exposed to this heat flux. This surface is exposed to this heat flux. Okay, at x equal to 0 is nothing but what, this surfaces. At x equal to L is nothing but this surfaces. So first this surface is exposed to the heat flux with that is of Q. Okay, and dissipates the heat by convection, and whatever the heat is conducted throughout this plate is dissipates its heat to the surrounding by the convection mode of heat transfer. Okay, so that is nothing but what, convection at x equal to L, at x equal to L. Okay, so with the heat transfer coefficient is H. See here, this is the H, that air heat transfer coefficient to the surrounding air at a temperature Ta, or you can say, you can take that T infinity or Ta. Now for these conditions we have to write the mathematical formulations of this problem for determination of one dimensional steady state temperature distribution within the wall. Okay, we need to find the write the mathematical formulations for the temperature distribution within this wall under these conditions. Okay, first what we have, what is this, one the plate other, so that there is one plate. Okay, a plate ಏನಾಗುತ್ತೆ, one it is kept in x directions, only one dimensional heat conduction, that is in only x directions. Okay, and x equal to 0, the surface is exposed to the heat flux Q, and when the x equal to L, this surface is exposed to the convection rate of heat transfer through this air. Okay, this is the conditions. So we need to write the mathematical formulation for the temperature distributions within the wall. ಈ ವಾಲ್ ಒಳಗೆ ಟೆಂಪರೇಚರ್ ಯಾವ ರೀತಿ ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಆಗುತ್ತೆ ಅನ್ನೋದು ನಾವು ಫಾರ್ಮುಲೇಷನ್ಸ್ ಮಾಡಬೇಕ್ರಿ. Okay, so this is the given formula. Only one directional heat conduction is there, that's why we have to take only in the x directions. If it is two directions, then we have to take x and y directions. Okay, so but in the given problem he has given only one directional heat conduction, then we have to take only one directions. Okay, that is x direction. Okay, so first we should know the governing laws of heat conduction. Governing laws of heat conductions. What is for one dimensional steady state? One dimensional steady state, d square t by dx square is equal to 0. Why it is 0? There is no heat generation within this element. Okay, so that's why for one dimensional is nothing but only dx square. If it is two dimensional, then we have to take a d square t by dx square plus d square t by dy square in the y direction also. If it is three dimensional, then we have to take d square t by dx square plus d square t by dy square plus d square t by dz square. Okay, but in the given problem he has mentioned that it is one dimensional steady state heat conduction. That's why d square t by dx square is equal to 0. So next, at x is range of this x is 0 to L, and that means x equal to 0 and x equal to L. Okay, so now we have to applying the boundary conditions to this governing equation. Okay, so first kind of boundary conditions we have to apply. What is that first kind of boundary conditions? That is the temperature distributions, a prescribed temperature boundary conditions. Okay, at x equal to 0, what happens here? The heat flux which is equal to the conduction. Heat flux is equal to heat conduction into the plate. So that x equal to 0 iddaga, what happens here? Heat flux which is equal to the heat conduction into the plate. So for this we have to write the equations. Okay, and x equal to L iddaga, at x equal to L iddaga, so what happens? Here? The conduction in the plate is equal to convection. That conduction is equal to heat conduction from the plate is equal to heat convection to the air. Okay, so heat conduction from the plate is given by conduction equations, that is k dt by dx at x equal to L, which is equal to what? H T x equal to L2 minus T A, that is air temperature. Here these two are the governing equations for heat conduction, and this is governing equation for the heat convections. Okay, we discussed about these two in the previous classes. Okay, this is the governing equations for the heat conduction, and this is the governing equation for the heat convections. Now heat conduction from the plate, that is minus k dt by dx at x equal to L2 is equal to heat convection to the air. Here if you observe this figure, conduction is equal to what? Convection. Whatever the amount of heat is conducted through this plate is equal to convection to this air. With the air is having the T temperature at TA and the heat transfer coefficient of H. That is what here the H T at x equal to L minus TA. That is the air temperature. Okay. Now we have to simplify it. So minus K dt by dx is equal to H T x equal to L minus H T A. Okay, so here again we have to simplify it. H T x equal to L, just we have to take this term to this side, then it becomes plus K dt by dx. You have to take this term to this side, then it becomes H T A. So this is what the temperature distributions within the wall. This is the mathematical formula for the given conditions. ಇಷ್ಟಾದರೆ ಈ ಪ್ರಾಬ್ಲಮ್ ಮುಗಿತ್ರಿ. Okay, so this is what the mathematical formulations of heat distribution within the wall. Within this wall, how much is heat is distributed? This is the mathematical formulation. Okay, so this is this will complete the first numerical. What he has given first, according to the given statement, we have to draw the one. There is one plate with with thickness of L, and one side, that x equal to 0. When the x equal to 0, what happens? that this surface is exposed to the heat flux, that is heat flux. Okay, so after that it enters to the plate. What happens here? The conduction mode of heat transfer takes place throughout this plate. After at x equal to L, what happens? This conduction will expose at the surfaces to the convection of convection to the air. Air is having the T infinity or TA temperature, and we having the heat transfer coefficient, convection heat transfer coefficient of H. So we have to apply the boundary conditions to this equations and formulate this. Okay, so this is first problem. So next one is the consider second formula. Consider a one-dimensional steady-state heat conduction in a cylindrical wall. So in the previous one it is the what it is one plate. Here it is one plate. So in this problem he has given one cylindrical wall with the inside radius r1. This is the inside radius r1 and the outside radius r2. Okay, the inner surface is heated uniformly at the rate of q1. So this here, whatever this here, q1 is representing the inner surface of the cylinder wall. The inner surface of the cylinder is heated at the rate of what? q1. Okay, watt per meter square, that is heat flux. The outside surface is contact with the fluid with heat transfer coefficient H to the surrounding air temperature T. Okay, write the mathematical formulation for this problem for the determination of one-dimensional steady-state temperature distribution within the wall. So it is similar to that of the previous problem number 1, but in that he has given one plate, but in this he has given one cylindrical wall. Okay, so here cylindrical means it is having two radiuses. One is at the radius of two walls. One is at the radius with r1, and the another radius, outer radius is outer wall is at radius of r2. Okay, inside this we are having one heat flux. Okay, we are having one heat flux. So that heat flux will supply the heat to this wall, and it goes throughout the these surfaces and exposed to the air by the convection mode of heat transfer. Okay, so which is having the heat transfer coefficient is H, and the air temperature, surrounding air temperature is T. So what happens here? You'll note when the cylinder the okay, inside layer of the cylinder is R1 radius. Okay, and outside radius ಎಷ್ಟಿದ್ರೆ R2 ಅದ. So inside this cylinder ಏನಾಗುತ್ತೆ heat flux ಅದ. So that is nothing but what? Heat is supplying. Heat supply ಆಗ್ತೀವಿ inside ದಿಂದ. So ಅದೇನಾಗುತ್ತೆ ಕಂಡಕ್ಷನ್ ಆಗುತ್ತೆ ಇಲ್ಲಿಂದ ಕಂಡಕ್ಷನ್ ಆಗುತ್ತೆ. ಸೊ ಕಂಡಕ್ಷನ್ ಆಗಿ ನೆಕ್ಸ್ಟ್ ಇಲ್ಲಿ ಹೀಟ್ ಬರ್ತದಲ್ರಿ, ಈ ಸರ್ಫೇಸಸ್ ಏನ್ರಿ ಎಕ್ಸ್ಪೋಸ್ ಟು ದ ಅಟ್ಮಾಸ್ಫಿಯರಿಕ್ ಏರ್ಗೆ ಎಕ್ಸ್ಪೋಸ್ ಆಗಿರ್ತದೆ. Okay, and that air temperature is mentioned here, that is TA, and that convective heat transfer coefficient he has given that H. So for these conditions, whatever he has given that these conditions, we need to write the mathematical formula. Okay, so here it is one dimensional heat conduction equations, and he has given that cylindrical wall. So for that we are having the governing equation for one dimensional steady state. 1 by r d of dr into r dt by dr is equal to 0. This is the governing equations for the cylindrical wall for one dimensional steady state equations. Already we derived these equations in the previous classes. Okay, so that is that derivation is for the three dimensional equations, but for this problem he has given it only one directional heat conduction equations. Then we have to take only the radius, that is only one directional equation. Okay, that is 1 by r d by dr into r into dt by dr is equal to 0. So if you go through the derivations in the previous class, we will find this term in that three dimensional heat conduction equations. Okay, there are three terms are there, but here he has given only one dimension. Then only so that we can take only one equation here. So now we can write here at R1 is range to R2. The range is R1 to R2. That is R1 is equal to or less than or is equal to or less than R2. Okay. So then it becomes what, d by dr or dt by dr is equal to 0. That just we have to take this term to this side and it becomes multiplied with the 0, then it is 0. Okay. Now boundary conditions at r is equal to r1. See here at r, whatever this r is there, this r you can check that this r is equal to r1. So what is the condition what is the boundary condition at this position? Okay, that is heat flux. So whatever this heat flux, which is equal to what, heat conduction into the cylinder wall. So at this conditions what happens, the heat flux is equal to heat conduction through this wall. ಎರಡು ಈಕ್ವಲ್ ಆಗ್ತವ್ರಿ ಅಂದರೆ ಹೀಟ್ ಫ್ಲಕ್ಸ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ಹೀಟ್ ಕಂಡಕ್ಷನ್ ಥ್ರೂ ದಿಸ್ ವಾಲ್. ಹೀಟ್ ಏನಾಗುತ್ತೆ ಇಲ್ಲಿ ಕಂಡಕ್ಷನ್ ಆಗುತ್ತೆ ಅಂದರೆ ಇಲ್ಲಿಂದ ಈ ಕಡೆ ಮೂವ್ ಆಗುತ್ತೆ ಯಾವಾಗ ನೀವು ಹೀಟ್ ಫ್ಲಕ್ಸ್ ಇದ್ದಾಗ ಹೀಟ್ ಸಪ್ಲೈ ಮಾಡಿದಾಗ. ದಟ್ ಈಸ್ ವಾಟ್ ಹೀಟ್ ಕಂಡಕ್ಷನ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ಹೀಟ್ ಫ್ಲಕ್ಸ್ ಈಸ್ ಈಕ್ವಲ್ ಟು ಹೀಟ್ ಕಂಡಕ್ಷನ್ ಇನ್ ಟು ದ ಸಿಲಿಂಡರ್ ವಾಲ್. ಓಕೆ, ಸೊ ನೆಕ್ಸ್ಟ್ Q1 is equal to minus K dt by dr at R is equal to R1. See here at R is equal to R1, heat flux is he has given that Q1 and the heat conduction is already we know that the equations that is K dt by dr into R is equal to R1. At R is equal to R2 what happens at this position? At R is equal to when R is equal to R2 and the E boundary condition ದಾಗ ಏನಾಗುತ್ತೆ ಇಲ್ಲಿ heat conduction ಇರ್ತೈತಲ್ರಿ, that is equal to the convection, that is equal to the surrounding convections. Both are equal here. Heat conduction from the cylinder wall to the heat convection to the air. Heat convection to the air. Okay. First one ಏನಾಗುತ್ತೆ ಇಲ್ಲಿ heat flux is equal to heat conduction. Next heat conduction is equal to heat convection. Okay. We have to write the equations here. Heat conduction from the cylinder wall is at R is equal to R2 ಇದ್ದಾಗ K minus K dt by dr at R is equal to R2, which is equal to heat convection to the air is given by H d T R is equal to R2 minus TA. Again make the simplifications here. K dt by dr, just we have to take this term to this side and this term to the this side. Okay, what happens, minus K dt by dr at R is equal to R2 plus H T R is equal to R2, which is equal to what, this H into T. Just you have to take this term, it becomes positive. So this is the temperature distributions in the cylinder for the given conditions, and this is the mathematical formulations, okay, for the temperature distribution in the given cylinder wall. Okay, this is complete the second problem. Okay, nothing is there in this, both first problem and second problems are same. Okay, just in the first problem he has given one plate, in this second problem he has given one cylinder. Okay, so in the third problem, derive an expression for one dimensional steady state temperature distribution T of x in a slab. He has given one slab here, T of x in a slab of thickness L for following conditions. Okay, there is one slab, and which is having the thickness of L. Okay, heat is generated in the slab at the constant rate of G naught. Okay, so in the previous problem there is no internal heat generated, he has not given any internal heat generation, but here in this problem he has given that heat is generated in the slab at the constant rate of G naught watt per meter cube. The boundary surfaces at x equal to 0 is kept insulated. The boundary surfaces at x equal to 0 is kept insulated. Then this surfaces get kept insulated. Insulated is nothing but what? There is no heat transfer from surrounding to the slab or slab to the surrounding. This surfaces get insulated. Okay, and x equal to L, here at x equal to L is kept at a 0 temperature. See here, at one surfaces x equal to 0 it is get insulated, and also at x equal to 0 this surface is also get kept at 0 temperature. There is a no temperature at these surfaces. Okay, assume constant thermal conductivity of the slab is constant. Give the relation for the temperature of the insulated boundary. Okay, now we have to formulate the one formula mathematical formulations for this given conditions, and also calculate the temperature insulated surface temperature of insulated surfaces per K is equal to 40 watt per meter Kelvin, and G naught is equal to 10 raised to 6 watt per meter cube, and L is equal to 0.1 meter. Okay, first we need to formulate for the given conditions, then we have to substitute these values in that equations. We will get the temperature of insulated surfaces, okay. So what he has given, just we have to describe it in brief way. He has given one slab of thickness L, and one side of the slab is get insulated, and the other side is kept temperature is 0, there is no temperature. Okay, uh, so for this conditions we have to write the mathematical formulations, and after that we have to substitute these values in that given formulations, then we will get the temperature at this surface, temperature at this surfaces. Okay, so governing equation for this is d square t of x by dx square plus g naught k. So see here, in the first problems we used only this term, that is d square t by dx square, okay, is equal to 0. But in this given third problem, we are using, along with this we are using this term. Why it is so? He has clearly mentioned heat is generated in the slab, so that we have to use this term. Okay, so that is d square t of x by dx square plus g naught plus g naught by k is equal to 0 at 0 to L range. This is the governing equation for this given slab. Now applying the boundary conditions here, dt of x by dx is equal to 0. So this is whatever the temperature which is maintained at t of x, so that dt of x by dx is equal to 0. Why it is 0? Because of there is a no heat change in or interaction to the surrounding to the slab or slab to the surrounding. That's why it is the dt of x by dx is equal to taken as 0. Then it becomes t of x is equal to 0 at x equal to L. So at x equal to L, at this process, he has mentioned that at x equal to L is kept 0 temperature. That is what t of x is equal to 0. So these two are the boundary conditions. Okay. Now integrating the governing equations, whatever the governing equation is there, that you have to integrate with respect to the x. We get the dt of x by dx plus g naught of x, g naught of k into x is equal to c1. Okay, d square t of x by dx square is there. So integrating up this term, we will gives the only dt of x by dx plus, so this is what g naught by k is there. Integrating with this term, that will give us g naught by k into x is equal to, this is the c1, integration constant is c1. Okay, now applying the boundary conditions to this formula, to this integrating governing equations. So what is that? First boundary conditions here, dt of x by dx is equal to 0. Okay, dt of x by dx is equal to 0, and also x equal to 0. So substitute these two value in this equation. See here, dt of x by dx is equal to 0 and x equal to 0 ಇದ್ದಾಗ ಏನಾಗುತ್ತದೆ, c1 is equal to 0. Substitute x equal to 0, and this 0 plus 0 is what? c1 is equal to 0. This is our required value, that is c1 is equal to 0. So integrating again, so again we have to integrate this equation. So we will get that dt of x by dx, integration of this term is t of x is equal to minus g naught of k into x square by 2. Integration of x is x square by 2 plus c1 of x plus integration constant, that is c2. So integrating again this term, we will get these equations. So again applying the boundary conditions, that is t of x equal to 0. Second boundary conditions is here, t of x is equal to 0 when x equal to L, that we have to applying the given integrating equations, that is t of x is equal to 0 and at x equal to L. So t of x is equal to 0, but here it is 0, and x equal to L, then it is becomes g naught L square. X is the x ಇದ್ದಲ್ಲಿ ಏನು ಮಾಡಬೇಕ್ರಿ, L substitute ಮಾಡ್ರಿ, this becomes L square by 2, which is equal to, so already we are having this c1 values, that is substitute here 0 into x is 0 plus c2, then it becomes what happens here, G naught, just we have to take this side. Okay, G naught by K L square by 2 is equal to C2. So we get the value of C1 and we get the value of C2. So substitute C1 and C2 in this equation. Then T of x is equal to minus G naught by K x square by 2 plus C1 of 0 plus plus G naught by K into L square by 2. So this is the C2 value again here substitute. Now this is the mathematical formulation for the temperature distribution in the slab. Okay, we need to find out the temperature of that by given values. So in the problem he has given that K value he has given, G naught value is given and L value is given. So substitute this G naught, K and this L value. Okay, so that K is equal to 40 watt per meter square Kelvin, Q naught is given, that is 10 raised to 6 watt per meter cube, L is equal to given. Okay, substitute all. Before that we have to simplify it here. We will get that T of x is equal to G naught by 2K into L square minus x square if we are simplified it. Okay, again in this equations we have to substitute all these all these value. So T of x G naught is given by here 10 raised to 6 divided by 2 into 40 here is given K 0 L is 0.1 square minus 0 square, we will get the 125 degree Celsius. T of x is, that is temperature at this surface is what, 125 degrees Celsius. Okay, so this we will completed 3 numericals in this classes. Okay, so if you have any doubts then